So first of all, I'd like to thank David Peat for agreeing to this interview. We're here to talk about science, religion, and related topics. In particular, we're going to talk about David Bohm. And so to start us off, David, I'd like you to tell me a little bit about David Bohm, his early background, and the influences that he had, maybe, up to the point where he went to university.
Okay, well, his family came from near Hungary, and his father emigrated, was pretty poor, and was a sort of itinerant salesman, settled down in a little mining place called Wilkes-Barre. And that's where Dave was brought up, and went to the local high school. I think he was an unhappy childhood because his father was a used furniture salesman. His big ambition was that Dave should have the biggest used furniture shop in Wilkes-Barre. And Dave thought otherwise he wanted to do science, and science was thought to be airy-fairy and not important. And Dave's mother was also mentally unbalanced. They called her schizophrenic, but later on other people thought maybe she was manic-depressive. But she spent time in mental hospitals. So Dave never felt he was properly mothered. And he always, later in life, thought mother and matter have the same root. So somehow I was never welcomed into the world of matter. And there was an aspect of Dave you think was a little bit like a spirit that was never fully grounded in the body. So anyway, and the other aspect was that he got some science fiction books when he was young, like magazines somebody had left, and read about those and had fantasies of going to other planets. He even wrote his own science fiction stories. So the way was maybe the world wasn't such a nice place, but you could go up into space and travel. And even when he was at school, he wrote his first unified theory of the universe. And this was a theory of mind and matter. So right from the beginning, mind was present. You mustn't have a theory that leaves out mind. The thing was a whole. So then he goes to university and ends up working with Oppenheimer. And Oppenheimer became an important father figure for him. His own father really didn't respect what he did. Oppenheimer, treated him with a lot of respect. He was very smart, and so he was a sort of father figure. But at the same time, we're talking about the 1930s, the rise of fascism in Germany, and Bohm notices a lot of anti-Semitism on the rise, and he feels the only people fighting that are the Russians. And he thinks about the Russian experiment, reads Marx. A lot of intellectuals around that were doing that at the same time. He has a girlfriend, Betty Friedan, who later became an important feminist, and they go to Communist Party meetings, but he finds the meetings a bit boring, so he stops going. But he does embrace Marx, and he's also doing physics. And one of the things he thinks about is that somehow this revolution can change human society. And if society changes, then human consciousness will change. So he's already thinking about changing consciousness. How do we change human consciousness? Maybe by having a rational society. So that means, one thing means that it must be rational all the way down to the atom and the electron, must have a rational theory. And the other thing he thinks about is how can there be freedom for the individual if you have the collective? He's thinking about that. And at the same time, he has a problem in physics. How do electrons behave in a metal? And he tries something ingenious. He says maybe the electrons are both individuals and both collective at the same time. So he finds that if you have things called plasma, which is like vibrations of the whole gas of electrons in the metal, these plasma acts to shield the interaction between individual electrons. So individual electrons become free in the collective by contributing to the collective. So this was a vision. Really, it was his first important piece of contribution was the theory of the plasmas, which really set the groundwork for a lot of work in solid-state physics. I mean, it's very important work, the plasma, but it came from his concept of trying to think about the society in which there was free individuals contributed towards the collective, but remained free. So that was his first important piece of work. We should maybe talk a little bit about quantum mechanics. Yeah. Well, quantum mechanics was developed by Heisenberg, Schrödinger, people like that. But the big important thing was that what did it mean? And Heisenberg says the meaning lies in the mathematics. All you do is the mathematics. But Niels Bohr in Copenhagen would bring these people together. He'd bring in Pauli, Heisenberg, Schrödinger, other people to Copenhagen to talk and thrash this out. And his view was that in order to when scientists get together, they have to talk like you and I are talking. You use ordinary language, maybe with a lot of technical words thrown in, but it's just language, nevertheless. And Bohr makes the point that our languages, human languages grew up for human beings of a certain scale. They're living on a planet with gravity. And so they contained a lot of hidden assumptions about the nature of space and time, and also about causality, what causes things. So whenever we speak, we're importing these notions. Whatever we talk about, inherently we have some idea of duration, time, location, the idea that things close together may have more interaction than things far apart, and these general ideas. And Bohr says, well, as soon as we try to talk about the quantum world, we're importing foreign concepts that don't really belong there. So what happens is we start to get confused, and we get paradoxes. So his thought was that there's a limit to what could be said at this quantum level. There's a limit to how far we can go without running into confusion. So he sort of puts a barrier in the Copenhagen interpretation. To give one example, you have something called the Heisenberg uncertainty principle. It tells you if you measure one property like speed, you then measure the other property, position, and somehow the speed becomes uncertain. And Heisenberg tried to argue that what you're doing is you're interfering with the universe. You measure one thing, when you try to measure the other, you interfere with the first. And Bohr argued against this strongly and said, no, you've assumed the electron actually has properties. It has a position, it has a moment, but that's not true. All we can say is that the result of our inquiry into nature gives us an answer. Inquire into nature another way, you get a different answer. And quantum mechanics correlates the two. But you can't say that the thing has properties. Or if I observe an electron here, and later on I observe it over there, I can't say it has a path. Right. I can't say it goes from A to B. All I can say is we saw it, there was an event here, an event there, and quantum mechanics allows us to correlate these two events. So, I mean...
We're now going to look at Heisenberg's uncertainty principle. In the classical domain, on the human scale of things, energy can have any value and appears to be continuously variable. We can easily determine, for instance, the position and momentum of a cricket ball moving through the air. On the other hand, at the subatomic level, energy comes in discrete steps or chunks. They're known as quanta. Each chunk or quanta is a multiple of a thing called a Planck constant, which is given the symbol h. This was discovered by the physicist Max Planck. Now, when he discovered this, it was very surprising, because what it meant was that when you tried to measure the momentum and position of an electron, the more accurately you knew the momentum, the less accurately you knew the position, as shown by this equation. So, there's a fundamental uncertainty at the subatomic level about how much we can know about two things at one time. Now, h also shows up in relation to this equation, E equals mc squared, which is probably the most famous equation in the world. H is the Planck constant and V is the frequency. If we multiply the frequency by the Planck constant, we get the total amount of energy in the system.
These two events. So, I mean, so the idea is that Bohr, people are asking, well, what is quantum reality? And Bohr's almost saying, that's not a good question to ask, because you're only going to get involved in confusion. Right. And all you can say is that mathematics allows you to correlate this and that. To go beyond that, you're going to have interpretations and they're going to arouse confusion. And Bohm tried to be faithful to this Bohr theory when he wrote his book Quantum Theory, which is an excellent book. And also because he was with Oppenheimer had worked with Bohr. So he was getting it right second hand, but I mean as close as you could to the authentic thing. It also helped give some lectures, so he knew exactly the Bohr interpretation. And after writing the book, he felt dissatisfied, and he felt in a way there was a sort of mystification involved, that that by saying you can't, there's a level beyond which we can't go. There's a limit to what we can say. And he felt, again, if we want to have this change of consciousness by changing society, reality has to be somehow tangible all the way down. There has to be a reality all the way down. So that's when he went on to develop what he called his hidden variable theory. And he also at that time was having discussions with Einstein. Maybe we could touch on that.
Sure.
Well, it may not follow logically from what I've said, but the idea Einstein felt there could be a unified theory for the whole universe. Right. That's what he was looking for. For example, unifying electricity, electrical forces with gravity. So he's looking for a unified field theory. And Bohm says it's taken us 300 years to discover the quantum level. So it's very much hidden from us. The classical level works so well, it took us a long time, and below the quantum level could be another level. May take a very long time to find that. And below that another level. So his notion was there are endless levels to reality. Endless levels, and Einstein felt no, that there can only be the one unified theory. So that's again a very subtle difference between the two, and an interesting one. Bohm's notion that he would talk about reality and say, well, reality is something that includes us, the observer. It's what we observe, the world we live in. But beyond that is that which is. And that which is includes reality, includes our constructions, but goes beyond them. One of his colleagues said it's like a spiral. Bohm thinks about this, and he goes way over there. I think he's forgotten, and he goes way over there, and he comes back to here again, but in a new way. Yeah. So at one time when he talked to me, and he was also discussing it with a person who'd written a book on Hegel, because Hegel was a big influence on him too, and was white. So was Whitehead. There was a big influence as Hegel for the dialectic, and Whitehead for the idea of process. And he did say, well, reality is something that we've helped to construct, but beyond reality, there must be something more objective, that which is, which includes the conscious mind. Okay, well, the hidden variables, it really began because Bohm was dissatisfied with Bohr placing a limit on what could be said and how far you could go. And he also felt it was important that people should realize that something was real and tangible all the way down. So he struggled with this, and to try and develop a theory which would really complete quantum theory. And there had been a long series of arguments between Bohr and Einstein. Bohr said essentially quantum mechanics is complete. There's only one interpretation, that's the one sort of more or less he created, Copenhagen. And Einstein said, no, there must be some way of completing quantum theory. So those were the arguments, and Bohm was aware of these because he would talk to Einstein about it. And so he went on to develop a theory in which, essentially what you could say, there are hidden variables. There are variables which will explain the quantum theory in a more realistic way. So you could call it a realistic interpretation or a hidden variable is a bit of a problem because later on von Neumann, the mathematician, came along and proved there could be no hidden variables. But he meant hidden variables in the sense of little tiny subparticles which were knocking the electron around, so it appeared to be random. But Bohm's was a little bit maybe closer to the idea of the plasma. But anyway, it was a theory that he was very excited about. He thought this will put the cat amongst the pigeons. Okay, so he was going to publish this, and he really thought the best thing that can happen is I'm going to be attacked, and I can defend myself in print, and there can be open debate, and finally we can open up quantum theory. Because one of his concerns had been that when Bohr summons Heisenberg and Schrödinger, all these people to Copenhagen, they resolve things too quickly. And he felt the important thing is to keep the question on the table, keep that creative tension. If you can keep a question open, you have enormous creative tension. The brain becomes very active, and maybe you can make it transcend something, leap through to it. Because he would sometimes think about that, you get blocked, how do you go beyond? Well, imagine that you've gone beyond. There's this gap, there's this like big, come to the edge of a cliff and there's land on the other side. You cannot jump it. So maybe imagine that you are on the other side. Maybe something will take you there. So that was his feeling. It was resolved too quickly and they should have held attention. So he develops the theory, and then a lot of unfortunate social circumstances happened to him, which maybe I'll mention. He was summoned before the Un-American Activities Committee, the McCarthy Committee, and asked to name names, and he refused to give names. So sometime later he was arrested and sent on the grounds of contempt of Congress, because he refused to answer questions, was sent for trial in Washington. As soon as this happens, Princeton University forbid him to set foot on the campus. Einstein says he would like Bohm to be his personal assistant, and Oppenheimer overrules it. And there's something behind that too, because Oppenheimer had done the Manhattan Project. He was desperate to be the director of the peacetime nuclear program. So he was prepared to do anything to do that.
Oh, and did he see Bohm as a bit of a threat?
He had given Bohm's name under it when he was being questioned by security services. He says, this man is politically suspect. Ooh. So he sold out people in order to get where he was. And sometimes Oppenheimer is seen as a tragic figure, but there was a part of him that was prepared to sell out.
Quite ruthless, in fact.
Yeah. And he also tended to insult people, denigrate them, people on committees, admirals, people like that. So they were out to get him, and he knew that. But anyway, and Bohm didn't realize that the father figure had betrayed him. Anyway, he goes for trial, and more or less, he's acquitted, or either it was dismissed or acquitted, but he does go to the process. comes back, and Oppenheimer sees him on the streets of Princeton and says, "You're still here, you must get out." So the word to Bohm was, "Get out of the country, you could be in danger." And at that time, there was serious thought that they would open concentration camps for communists. I mean, this was a thought in the States. People really feared that.
It was a witch hunt, wasn't it?
It's a witch hunt. It was a witch hunt, yeah. I mean, initially, they had to prove you're a member of the Communist Party. Later on, you had to prove that you weren't, that you never had an association. The burden of proof was on the accused person. So people really thought his friends could be rounded up. So we went to Brazil. While he was in Brazil, Oppenheimer called a seminar on Bohm's hidden variables. And the amazing thing is that several eminent physicists, some of whom are alive today, got up and said things like, "Bohm is a Trotskyist, Bohm is a fellow traveler, this is Marxist physics." So it's first of all attacked on political grounds. Yes. Then the idea was we've got to find a hole in the theory. And at the end of the seminar, Oppenheimer says, if we can't disprove Bohm, we must all agree to ignore him. Wow. Bohm didn't know this, but his paper comes out and he wonders why he's not getting any response. Wolfgang Pauli, who wrote to him, and they had an exchange, but very few people wrote. And the word went out, Bohm's wrong. And it's still around today. There are still people I'd meet, like eminent physicists, and they said, Bohm did the plasma, he did good stuff, but, really, this hidden variable stuff was wrong. And I say, well, do you know why it's wrong? And they say, well, no, I've not read the paper, but I just know it's wrong. So that has continued. As Bohm said, "I'll never convert those people. It's when they die off and the new generation comes up, then they may take it more seriously." So that was the first step. Just say that we've gone up to the point where Bohm is in exile. He's feeling very, very isolated, and nobody's responding to his theory, and more or less he's going to give that up. He gives it up, puts it in the drawer. It's a phase of his life that's over. But as it turns out, it won't be. Now, when he wrote the book Quantum Theory, there was a famous debate between Einstein and Bohr on Einstein felt that there should be a way to show quantum theory was incomplete. And he thought up a sort of mind experiment with two other physicists, Podolsky and Rosen. And it was called the Einstein-Rosen-Podolsky paradox. And it suggested that you took two particles and you move them apart. They correlate, you move them apart. If you do an experiment on one, certainly you're going to disturb it. But how can that possibly affect this one? So by experimenting on this, you can infer something about this without ever touching it. So somehow I must be able to know both the position and the velocity of this particle because I'm not disturbing it. I shouldn't be able to know those, and which quantum theory says you can't know it. So Einstein thought, fine, I found the flaw. I found a way of finding these two things which quantum mechanics denies, so it must be incomplete. And Bohr wrote a very subtle paper sort of saying that that's not true. And when he used this phrase, a disposition to make a measurement would change things.
When quantum mechanics was being formulated in the early 1900s, Einstein felt uncomfortable about how complete a theory it might be. In 1926, he wrote to Max Born expressing his misgivings. Quantum mechanics is very impressive, but an inner voice tells me that it is not yet the real thing. The theory produces a good deal, but hardly brings us closer to the secret of the old one. I am at all events convinced that he does not play dice. The reason for his lack of confidence in the theory is exemplified by what became known as the Einstein-Podolsky-Rosen paradox, or action at a distance. For example, here is an initial radioactive particle with a spin state of 0. The particle loses some energy as it decays and produces an electron and a positron that move away from each other at the speed of light. In the process of being created, the electron and positron have become entangled or correlated because if we measure the spin state of the electron, we have seemingly fixed the spin state of the positron instantaneously without touching it. So the paradox is that as nothing can travel faster than the speed of light, there is no known mechanism to explain this phenomenon. This is sometimes referred to as action at a distance, or non-local effects, and quantum mechanics actually predicts this behavior. it was experimentally verified by Alan Aspect in 1986.
Now what Bohm did was he reformulated Einstein, Podolsky and Rosen's experiment in a very elegant way in the book. So first of all, he's reformulated in a very elegant way. And secondly, he's written a paper on hidden variables. And a Scottish or Irish physicist, John Bell, read Bohm's paper on hidden variables and said, I saw the impossible done. He was amazed at that. And that got him thinking about the experiment that Einstein had proposed. So he thought about it, and he wrote it down mathematically in such a way that it could be tested. It was called Bell's inequality. And several people read that paper. One of them was Alan Aspect in Paris, and he actually did the experiment where he took two particles, they went far apart, several meters apart, and did simultaneous measurements and found they were correlated, even though they were great distance apart. So that introduced something new into quantum theory. It was the idea of non-locality, that they can't be linked by any force or any field. It must be a new sort of, you call it correlation or co-relationship. And what is said is maybe quantum theory is a passing theory. Maybe, there'll be another one in a century's time. But that fact about the universe is an experimental fact. It can't be ignored. So whatever comes later, you have to have this idea of non-locality, which was really abhorrent to many, many physicists.
Is it possible to say how many particles in the universe are correlated to some degree?
Yeah, that's a more difficult thing. I mean, the idea would be you have something that's together and you pull it apart, but then if you thought of maybe the Big Bang, everything was correlated at one time or another. I don't fully understand that one, no. And I'll tell you another thing, it's very difficult, we talked about language, very difficult to talk about two particles being far apart, because you use the word far apart, and then you say they're correlated and you immediately think of something between them, correlated. I mean, as we talk, we have the limits of language to try and talk about that thing. But certainly they're correlated. The other thing that you have to be careful about is if you try to, the nice idea would be you want to shake this one, and this one's going to shake as well. Then what you've done is you've sent information about here over to here at faster than the speed of light instantaneously. And you can't do that, because as soon as you shake this one, you break the correlation. So people, when this came out, some people said, oh, that could maybe explain how minds are connected, because there was somehow my mind, I can do something in my mind, it'll do something in yours. But immediately I do this, it will disturb.
It breaks the link.
It breaks the link, yeah. And we can come back to discuss that in terms of how Bohm's hidden variables developed, because that can then explain that again.
So let's talk about undivided wholeness as being the next adjunct.
Well, that's not really unique to Bohm. It was present for Niels Bohr too. And also Wolfgang Pauli, who was really one of the great physicists of the 20th century, talked about the intuitive sense of wholeness, or the intuitive grasp of wholeness. Well, for Pauli, wholeness was the essential thing in quantum theory. For Bohr too. You can see it in one way to explain it is when you make a measurement. In our world, you can make a measurement and the observer doesn't have to interact very much with what's observed, But in the quantum theory, your observer and observed are linked by a single quantum. And this quantum can't be divided. So at the moment of observation, the observer and the observed are linked together and form an undivided whole. So that's the very essence of the theory. Okay. And someone like John Wheeler, who was a student of both Einstein and Bohr, would say that we look at the world, for centuries we looked at the world behind a 4-inch plate glass. And now we've smashed through the glass and we've reached in and touched the world. Oh, okay. And he says, cross out the old word observer and put in the new word participator. Right. So it's a participatory universe. Right. Our interrogations, our acts of observation actually change the universe. So that's the universe we live in. And then Bohm would grasp that too, undivided wholeness. He would go further, because in wholeness he would also include mind or consciousness. Right. That's an indivisible from matter.
And in fact, most of the physicists of, say, in the 30s or 40s would not really include mind as being part of that participation.
The only one who would have done would have been Pauli. Okay. And Pauli did struggle. Pauli had a breakdown at the age of 30 and went to see Carl Jung. And afterwards had a remarkable series of dreams and felt that it was important to develop a unified theory of matter and psyche. And he also talked about the resurrection of spirit in matter, that spirit died 300 years ago. With Newton and Descartes. And we're now at the age where spirit will return. So he really was very strong on the unification of matter, psyche, and spirit. So he was pretty unique. And then Bohm, of course, too. This sense of undivided wholeness.
Including mind and matter.
Yeah, including mind and matter. But important in undivided wholeness, and then he would talk about our present age of fragmentation. You know, things are fragmented apart, countries are fragmented, disciplines are fragmented. But within wholeness, so his idea of fragmentation was twofold. One is you break apart things that belong together. The other thing is you artificially put things together that shouldn't be together. So within divided wholeness also implies you can have individuality. So wholeness implies, yes, that things can emerge out of the whole that have their own sort of boundaries. And if you try to force them together in artificial ways, that's fragmentation too. So it's important to remember fragmentation just doesn't mean splitting up. It can mean putting things together that shouldn't be there. So, but anyway, that was his notion of wholeness was something that went right throughout his life. And in a sad way, you could say maybe that's, as some friends had said, maybe that's the one thing he was not able to achieve in his own personal life, that sense of wholeness.
Also, from what I've read, it seems that Bohm had a unique way of internalising some of his ideas in that he would actually sense them to some extent in his body.
He talked to Einstein about that. He would say that my body is created out of the same matter as the universe. And I can find out about the universe by looking outwards in the laboratory or through the telescope or looking inwardly in my body. And he would at times talk about having sensations, internal sensations, which seemed to indicate to him how things were. So he had sensations in the body. And he talked to Einstein about that. And Einstein said when he thought about space-time, he had a little rubber ball that he'd squeeze, and it would produce sensations in the muscles. And that led him to insights, or it helped his thinking. Right. So both of them thought very much, partly were thinking through the body itself, the physical body. And with the tensions, he would talk about the tensions in the body and how these can manifest. Also, of course, he would also think that things like memories and thoughts and traumas could be trapped in the body. And that the practice of yoga, the ancient practice of yoga, the original ancient practice of yoga was like to see these flows going through the body and to encounter these blocks and free them up.
So I'd like you now to tell me how Bohm got to the idea of the Implicate Order.
Okay. Well, he's left Brazil, he went to Israel. From Israel, he moved to England and was first of all at Bristol. And when he's in Bristol, he's thinking very hard that the fact that there's two theories of science. There's one is quantum theory, which deals with the very small. The other is relativity, which deals with speeds close to light, with big things, the universe, black holes, all of that sort of stuff. And these two don't link together. And there have been many, many attempts to build bridges between them. And they've all sort of fundamentally failed. But he thinks about it, and he has arguments where he feels that somehow quantum theory in some ways depends upon relativity, because you need large-scale apparatus to make the measurements. And relativity in some ways depends upon quantum theory, because if you want to map out space, you need rays of light and you need atomic clocks. So the two, in a practical way, both theories depend on each other, but they're sort of independent. And physicists are saying we need a new idea. And they're saying we need a new theory, and they say we need new mathematics. And Bohm says, no, it's much deeper than that. We need a new order to physics. So that's what he feels, we need a new order. Not just a new idea.
Okay, let's just examine this word order, because it's not necessarily clear to many people exactly what we're talking about. So would an example of an order maybe be the acceptance, for instance, of a space-time framework that, say, Newton had originally postulated, and which, to a large extent, we still base a lot of our thinking and a lot of our language on today?
Yes.
That's one type
yes.
of order.
Bohm would call that the Cartesian order, because Descartes showed you could represent a point in space by three numbers, and then you can, after that follows algebra and the differential calculus. So that's an enormous order which was carried through into quantum theory of relativity, and he felt that just doesn't apply. The notion of continuous space, of points, of the calculus, none of that really applies to quantum theory. You need a completely different. So order is much wider than a theory. Right. He said there can be revolutions in theory, but underlying that can be the same order. Same as in a country, you can have revolutions, but the same, much deeper sort of order can remain in a country.
All the cultural things and the disposition to end up with a dictator, for instance, might remain unchanged. So you might get rid of one dictator, but just...
Right, or here in Italy, the government keeps changing, but underlying that is the same sets of relationships between people, dependencies and favours and things.
So things don't really change.
Yeah.
Okay.
And that was his feeling too, that when people said there's a revolution, in fact, not all that much necessarily changed.
So this takes him into developing these ideas behind the implicate order, or what the implicate order might be.
And in fact, what happens is that he's, again, we said like his big thing was you've got to hold the question. So he was holding the question, and somebody writes to him who's read one of his books, and it's an artist called Charles Biederman. Starts writing to Bohm, and they have this long, long exchange over several years of correspondence of thousands of letters. And Charles Biederman has written a book called The New Cézanne. So he's interested in you could say the order of painting, how it changed from, more or less classical perspective to Monet, the first big impressionist, then to Cézanne, and finally to Mondrian, who just had things, just squares and lines. And Biederman talks about how the order of painting changed. And he really believes that when this changes, human consciousness changes with it. And he's starting to write these ideas to Bohm. Okay. And Bohm's saying, well, if I could find the mathematics that would describe, or the algebra that describe an impressionist painting, that's exactly what I need for quantum theory. Right. I could just tell the famous story. There's a story told about Cézanne that he painted Vollard, the art dealer, and there were hundreds of sittings. And he's nearly completed the painting, except there's a little bit on the waistcoat, or one of the hands that's incomplete. And Cézanne tells Vollard, if I'm to paint that, I must repaint the whole of the painting, because each part contains the whole, and the whole is in each part. So Bohm hears this story, that the whole in the part and the part in the whole, and everything, this little area depends upon the context of the whole, and the whole depends upon this little area. And he says, if I only could describe that mathematically or algebraically, that would be the mathematics of quantum theory. So out of that exchange, I think part of that change was very profitable. He starts to develop the idea of the implicate order. So it maybe comes partly from that exchange, that stimulation of thinking with someone who's from a completely different field, which is really exciting, when that happens, when two people meet, who never actually physically met, only met through exchange of letters. And so maybe I could say a little bit about the implicate order. Yes. Well, what he would say is the world we live in, the world, you're sitting over here, I'm sitting there, we're separated in space. And we're two objects in space, and we're interacting, in this case, by speech, but we could interact by forces, by electricity or magnetism. He would call that the explicate order. And that's the order that's well described in Newtonian physics. He would say underneath that is the implicate order. And in the implicate order, everything is enfolded into everything else. So you could say that the water is in the jug, but also the water is contained in the jug, but also the jug then would be contained in the water. Things are enfolded in each other. And these are maybe best illustrated by images.
In the explicate order, we have a square piece of paper. It doesn't take much imagination to see that we could make this into something else, like one of these. All you need is the know-how and a fair degree of dexterity. So let's see the transformation. The implicate order contains all of the potential transformations of the original square piece of paper into very many different objects. Although the method of folding would be the same in each case, a precise sequence would have to be followed to create a specific object. All of those sequences are simultaneously present in the implicate order. The mind of the person doing the folding selects one of these and then follows the necessary steps to effect the transformation in the physical realm. Thus, the implicate order is seen as holding the potential information for all processes of transformation in both the physical and mental realms. This unity of implicate order and explicate order means that when anything changes in one, a simultaneous change occurs in the other.
So his notion is that and in the implicate order must also be included mind. So the implicate order is in a sense is the ground out of which the explicate comes. But an important thing about the implicate order is that in a certain sense of the word it's much bigger than the explicate order. So only certain aspects of the implicate can manifest themselves at one time.
So there's a lot more potential in the implicate order than we actually see around us, as it were.
So you take Niels Bohr's idea, take the idea in quantum mechanics. Some cases the electron behaves as if it's a wave. Sometimes it appears as a particle. These seem to be a paradox. A particle is located in space, a wave's distributed all out. And Bohr used this word complementarity for this. So introduced the notion of complementarity, that reality Quantum reality is so big that you can't exhaust it with one single explanation.
Right.
So you have complementary explanations. Interestingly, he got that from his father, and his father was a psychologist who read William James. And William James said the same thing about consciousness. Sometimes consciousness is little bits, and sometimes it's continuous. So it's sort of complementary aspects.
Yes, I mean, there are times when you remember a specific fact or a specific event or smell, and then there are other times when you remember how you felt over a particularly protracted period of your life. You may have been ill, or you may have been in love, or something like that. But nonetheless, you see that whole thing, but there are still parts contained in it as well.
So these are really interesting connections that if you think about it, that the study of consciousness influenced Bohr to develop complementarity, and we'll later see that another, when Bohm tries to get the algebra of the implicate order, that also comes from considerations of consciousness. So at this event, Bohr talks about complementarity, but now we see Bohm has given a reason for it. That the implicate order is so big, when you express it as the explicate, sometimes it comes out this way, sometimes it's that way, and these two ways appear paradoxical and placed together. They're complementary, because the underlying order, the underlying ground is so rich. It can't be exhausted with one manifestation.
So did Bohm go on to describe in what ways something is enfolded into something else?
He gave a number of metaphors for it. One was the metaphor of the holograph. If you take an ordinary photograph and you rip part of it off, you may just get a hand or a leg or an arm. If you take a hologram, and you break part of it off and you illuminate with a laser, you get the whole image back. I mean, maybe there'll be less resolution, it will be a bit fuzzy, but you get the whole image. So that the image, if this was a hologram, the image is enfolded over all parts of the hologram. So that also means that if you take a picture of my head, and here's one ear and here's the other ear, then in the hologram both ears are enfolded one over the other. So in explicate order, this ear and that ear are separated. In the hologram, they're united. So that also gives you the sense of non-locality. It's another way of looking at non-locality. The two electrons you pull far apart that remain correlated in the implicate order are together. They're enfolded over each other.
Okay, so in that sense, if I've got this right, then there's something, to follow this analogy, coming through the implicate order to, as it were, create the explicate order. Yeah. I mean, is that just raw energy?
Well, the implicate order would, in a sense, would have to be at some level non-material, or mind and matter united. So that's the implicate order. But then there's a bit of a critique about this, that in a way it sounds too Platonic. Plato said, how do you recognize a chair? Because it could be wooden, it could be upholstered. How do you know it's a chair? Because in your mind must be this notion of the ideal chair, which exists in some sort of, I don't know where. It doesn't exist in our material world, the form of the chair. So some people criticize Bohm, saying the implicate order was a bit Platonic, that everything emerged out of the implicate order, as if everything was there. What was its structure? So Bohm went on to think of what he called the super implicate order, that somehow the implicate order expresses itself in the manifest world, and there is a super implicate that becomes aware of that expression and feeds back into the implicate order. Okay, you could say that here's the implicate order. It's a vast, undifferentiated sea in a way. We don't know what the structure is. It manifests itself in the manifest world as maybe as an electron. Yeah. And the super implicate, in a sense, it's hard to find the right words, not so much observes it, but has an awareness of this, or sees how the manifestation has taken place in space and time. And so that information is fed back into the implicate order. So it would suggest that as the implicate order manifests itself in time, it gains in richness of structure. Right. Now, this is me talking, not David Bohm. Okay, this is me talking. Be very careful. Yeah. I'm not David Bohm. So I would say then, in the sense that it almost suggests an evolutionary nature to the implicate order. Right. That as it begins to express itself in space, time, and manifestation, the results of this, the results of these experiments or whatever, or feeling out of the manifest world, influence its internal structure. So the internal structure would be changing. Whatever is the structural principles of the implicate order.
We've got a system with some sort of feedback in it.
Yeah, that's
and
right.
Also
like a
system that seems to be, to use a technical term, the autopoiesis. That is, it's an act of self-making.
Yes, that's right. Yeah. And this is like you and I talking. I couldn't say if Bohm would 100% agree with it. No. But luckily he's not around to come and criticise us. Yeah, so that would be, that's taking you up to about no, it's gone a bit beyond the early 1970s, but then his book comes out, Wholeness and the Implicate Order, a bit later on. Okay, well, it happens this way. I mean, he's thinking about the implicate order and also beginning to think, sort of, is there a way to express some of this mathematically? And at the same time, he takes on a student. Anyway, one of them was called Chris Philippides, and Chris went back and read the original hidden variable paper. I think he talked to Basil highly about it and said, why has Bohm dropped it? And he said, oh, well, you know, it just never worked out. And Chris said, well, you know, I really want to work on this. So he had a friend who was working, I think, as a geologist or something like that, but they had a computer package which enabled them to look at landscapes. And so every night he would take Bohm's mathematics with this computer package. I suppose in those days computers weren't that fast either. But the idea was that Bohm's hidden variable theory said the electron actually was like a little particle, and it actually had a path. Remember what Bohr says is the electron is sometimes a wave, sometimes a particle, and you can't talk about the path. You can just talk about you saw it here, you saw it there, and quantum theory correlates the two measurements, but you can't say it has a path in between when you're not observing it. Bohm's theory was, yes, it does have a path. But at the time, you know, he was being capable of calculating what those paths were. So these guys worked late at night using a computer and worked out the paths the electron would have in a certain sort of experiment. They took it to Bohm, and I think Bohm was staggered, like to actually see this manifest, that yes, this accorded exactly with what was observed. This was a thing called a double slit experiment, where electron goes through two slits. Yeah. So they showed the trajectories, the path the electron could have, and they showed the pattern that would be on the screen. It was exactly right. So Bohm got quite excited at that point, and decided to work on the theory again. And he called it, first of all, hidden variables. Then he called it the realistic interpretation of quantum theory. Finally, he called it the ontological interpretation, ontology being the way things are. So this was a theory that says this is the way things are. And he now cast it in a new form, and in the following way, which is a little bit technical, to try and explain it, that the equation for quantum mechanics is called Schrodinger's equation, which enables you to calculate the wave function, which describes how the quantum system is. And in that, you'd have a bit which is a bit like kinetic energy, something like that, and a little bit to do with potentials. So how's the electron being pushed and pulled? Because the electron has a charge, and it may be being pushed and pulled somewhere. So those two were sort of more or less classical ideas that were in the thing. Well, Bohm did a way of transforming it, so essentially you've retained the theory, but it now has like a new, it's seen in a new light. It's like you take something, you see it in a new light. And the thing that was found to be added was a thing he called the quantum potential. That was a new feature. Now, if you talk about magnetism or electricity, you have a little bit of, you have a magnet and you have a little needle here. The closer you bring the needle to the magnet, the more it pulls, and then finally jumps out of your finger. So it depends upon the strength of the field. The effect depends on the strength. Now the quantum potential doesn't work that way. The quantum potential, the effect depends upon the form of the potential, you know, its pattern, if you like. So it's a completely original idea in physics. So now what he's got a theory in which the electron is both being moved by an ordinary potential, like an ordinary force, mechanically, like it may be being moved around by electrical charge, it may be in a magnetic field, and then the amount of movement or the effect depends on the strength of the field. But he's got another one, the quantum potential, which depends upon the form of the field.
And that would determine the path? That would
have to influence the path. Yeah, influence the path. Oh, so the other thing he's saying is what you have now is subtle energy. So he's introduced the idea of a subtle form of energy. So we can give a couple of metaphors here. One is the idea that you have an ocean liner in the fog, it's approaching a harbour. So it has this enormous power of the engines that are driving it forward, which is the metaphor for the force on the electron, because it's got a charge. And then you have a radar signal, which is an incredibly tiny amount of energy. Very tiny, but it contains a lot of information. And if you have an automatic sort of pilot system, that information is guiding the direction of the boat. So you have an enormous powerful engine, a great raw energy that's being guided by a very subtle energy, because the subtle energy is rich in information. So that guides the boat into the harbour. The same way with the electron. The electron's being pushed and pulled, but it's also being guided by this quantum potential. So in that way, you can explain all the results of quantum theory. You don't get anything different. It's equivalent theory, but now it's a very different interpretation. The electron really is an object. It does have a path, and it's being guided by this very subtle quantum potential.
Okay. And so what is this information that the sort of electron might be picking up then?
Yeah. So, why is the electron taking a particular path? Well, in fact, it's the information about the whole experimental arrangement, which is beautiful because, Bohr would say, you ask a particular question, that means you have a particular set of experimental arrangements, you get one answer. You ask another set of experiments, so you have another set of experimental arrangement in the lab, you get another answer. And now Bohm's saying that, in fact, what you have is, at the explicate level, you have an arrangement of matter, and at the implicate level, really what you've got is a field of information, and the electron is reading that field and responding to it. You have another as an arrangement in the explicate order, you have a very different set of information. At the quantum potential, the electron behaves differently. So essentially, the electron is reading information about the experimental arrangement. And maybe even greater, it's reading information about the whole cosmos. So it isn't a little tiny featureless particle. It actually has the ability to read information. And at this point, Bohm starts to talk about proto-mind. Okay. The electron is, in a sense, a proto-mind. It can respond to information like we can respond to information. So he would say that mind was there from the beginning. Mind isn't something that evolved at a certain level of complexity with organic molecules. It's there right from the beginning. Now, of course, you can have brains and nervous systems increasing complexity so that you have things like self-awareness. But the whole principle of mind was there right from the beginning. It's inseparable from matter. It's part of the electron. And just as the electron is reading the information about the apparatus, so our bodies, in a sense, have this very rich system called the immune system, which is about as complicated as the brain. And that is reading patterns in the environment, patterns of allergies and all sorts of things, yeah. So that's a pattern recognition system too. Yeah. So is the brain. So we have these complex systems throughout the universe, and beginning with the simplest particle, the electron. And then Bohm moves on for this. Earlier we talked about the implicate order and the explicate order. And then Bohm wanted to move to the super implicate. Now he wants to move to the super quantum potential. So at the level where he began, the electron is a little particle, it has a path. And that path is, in a sense, the energy for the path, the pushes and pulls could come from electrical fields, whatever, but the details of the path come from the quantum potential, which is information about the whole. So again, you have holism built in. You also have the idea of the aspect experiment. You pull two electrons apart, now they can both read the same quantum potential. So they're both reading the same quantum potential, they're both correlated. If you try to shake one of these electrons, you immediately disrupt the quantum potential, which is so rich in information, like you've just randomized it, so you've destroyed it all. So he also would use the word active information. The information is active, it's an activity, it's not a passive thing on a page, but if you try to disturb it, then you deactivate it. So now he develops the super quantum potential. What he says is in the first level, you could object to it, and physicists could object, saying, I don't want to go back to having the electron as a little ball moving along. I don't like that. We've got rid of that with Bohr. But now Bohm says, no, the electron is a process. And what is a process guided by the superquantum potential? So it's a process where the whole universe would collapse into this tiny area, expand out again, and collapse and expand. So the electron is constantly coming into being and vanishing, and coming into being and vanishing. So the electron now is a process. Maybe there aren't lots of electrons, there's just a process in which manifests here, manifests over here. So the aspect experiment, there'd be one process manifesting in two places, not locally. Right. So now you have this notion, maybe to extend it, which is very much going back to Vedic teachings, that the universe is constantly being breathed or sung into existence and going out of existence. It's constantly coming in and out of existence. That would also suggest consciousness is the same. There is no self.
Has to be created at each moment.
Yeah,
in a way.
It's created in each moment and dies away. It's created again. So that was the level at which Bohm was now trying to unify the implicate order and the quantum potential at this level.
So that's very interesting. Did Bohm ever develop any mathematics for the implicate order?
Well, he was really struggling to do this, and if you remember, he'd said that the old order was a Cartesian order of space and time and the calculus. So it has to go beyond that. And so he was looking at what are called algebras, and everybody did algebra at school. But a famous mathematician, David Hilbert, said algebras are the relationships of relationships. So the relationships of relationships. And he thought the answer must lie in algebras. And he and his colleague Basil Hiley really worked trying to discover what that would be. And part of that also would be that time had to come alive. The time in physics is often just a parameter. It often looks similar to temperature in some of the equations. Temperature is just a parameter. But as John Wheeler also said, you put your equations on the floor, the best equations, you wave the magic wand and say fly, they still stay on the floor. But the universe flies. So there's something magical about time. Time is truly dynamical. So that's the thing Bohm also wanted to bring in, somehow to bring in time, to find this algebra, to think about what they called pre-space, that somehow you want this structure that lies below space, time, and matter. And one of the things they found is what was called Grassmann algebras. So they were working on Grassmann algebras. And only later on did they know the story behind it, that Hermann Grassmann was a German mathematician of the 19th century. And he became very, very interested in Vedic teachings and taught himself Sanskrit. So he was a Sanskrit scholar. Interestingly enough, also was Schrödinger. Schrödinger almost gave up physics to study Sanskrit. So he's a Sanskrit scholar, and he wants to know what is the movement of thought, what is the movement of consciousness. So he develops an algebra for the movement of thought. And the idea is a thought comes up, dies down. Within that thought is another thought that comes up and dies down. So it was the emerging and dying down of thought, which he described in this algebra, which meant you had to have time in it. So this was the algebra that Grassmann did, and is present in his notebooks. But what mathematicians did was they extracted bits of it they thought was useful, and they left really this dynamical part out. So what would be taught in a course is really a sort of a shadow of Grassmann. So Bohm, it was very interesting that Bohm and Hiley are really trying to do what is the deep algebra for the implicate order, for the superquantum potential, for the processes of nature, and it turns out to be the same algebra that's the algebra of thought. And I think that's fascinating. Why? But so that was it. Bohm, died in the early 90s, and Basil Hiley's carrying on. So you could say they've not really achieved, the final answer. But a lot of people are moving in that direction. We need a deeper algebra.
Okay, very good. That sort of takes us on to our next section, our next topic, which is the problems of language. And certainly we've kind of barked ashes a couple of times at least in this, talk that we're having. And so I'd like you to say a little bit about Bohm's ideas on the sort of reifying function of language, the way it tends to fix things that aren't really fixed, and how he got on to what he called the Rio mode, which is more of a flowing type of description. So if you could tell us about that.
I think Bohm's interest in language goes back to either when he was a student or, after he got his PhD. I'm not quite sure the dates. But a book came out called Science and Sanity by a man called Alfred Korzybski. And it was very, very popular at the time amongst people like scientists. And it introduced the idea, what he called, of general semantics. So in part it was the notion of how do you convey information from generation to generation. In part how language works, and this very much interested Bohm. So his interest began probably with Korzybski, and a little bit remember his idea was how do you transform society? How do you, if you have a rational society, people behave rationally. So language has to come in at this level. So he's very concerned about those ideas. He was aware of a lot of Bohr's work on language. Later on, he had a student called Donald Schumacher, and Schumacher had read a lot of Wittgenstein and probably introduced Bohm to Wittgenstein and Wittgenstein's theories about language. So Bohm was very sort of sensitive to language. And one about the reifying thing, the fact that language works well if you want to talk about chairs and tables, but then you take things like feelings and desires and thoughts and emotions, and you treat them also as objects. So somehow the language makes them real. So what works well for practical things starts to causes a lot of problems. And then other people have said that. I think it was Lacan said that symptoms are words that are lodged in the body. So many people have talked about language like that, that language makes things appear to be real. It creates illusions. So this was his view on language. He probably also knew about a man called Benjamin Lee Whorf. and the Whorf-Sapir hypothesis. This was that language and worldview are intimately related. There's a book by a guy called Pinker called The Language Game, is it? Something like that, where he sets up a straw man type of thing and says that Whorf said that language causes the way we see the world. But Whorf never said that. He said there's a correlation between the two. So somehow the language we speak disposes us to see a certain sort of world, and the fact we've built this certain sort of world influences the language. So the two, it's a sort of circular thing. Yeah. And Bohm certainly knew about that. And I think he'd actually, at some time in his life, met a Navajo or Hopi man, and taught a little bit about that to them. So he was very aware of language. And one of the things that he came to see was that quantum theory really is about process. It's about movement and process and transformation. And the way our language works, when you say our language, most Indo-European languages, you begin with objects. That the Newtonian worldview is objects that interact. And so the language also reifies things. It says our world is made of objects, and these objects are independently existing, and they interact by forces and fields. But we know in the case of the electron, at least in the Bohr interpretation, that you can't say these are independently existing objects, that they're really, or even in Bohm's interpretation, they would be processes. In Bohr's interpretation, you really can't say too much about them because it's participatory.
So you've got this thing of hidden assumptions in a way in the language.
The language, yeah. And even Bohr has said that language places a limitation on how far we can go. If we go much further, we're just going to get involved in paradox. So Bohm tried to develop what he called the Rio mode, and from the Greek word means to flow. So it was a flowing mode. And the idea was it would be very, very rich in verbs. So it would be a process language. And that's what he wrote, that's what he tried to develop. He wrote a paper about it. He published that paper as one of the essays in Wholeness and the Implicate Order. And when he was involved in the Brockwood Park School, this was Krishnamurti School in England, he would try with the staff and students to actually speak the Rio mode. But it never really worked. And as people said, in fact, what we ended up is using the verbs as nouns. We're so conditioned to speak in a certain sort of way. And I know the few linguists I showed the paper to didn't think much of it either, because they would say you can't create an artificial language. Right. No, it's not possible to.
It's a bit like Esperanto never took off.
Yeah, but this was far, far beyond Esperanto, because you were going to get rid of nouns. Now, what happened at the end of the last year of his life was quite interesting, because I had been involved with some Native American groups, in particular a man called Leroy Littlebear, and we arranged to have a circle of a dialogue or a discussion circle with native elders and Western scientists. And we held that at a place called the Fetzer Institute in Kalamazoo. And it so happened by coincidence, David Bohm was scholar in residence there at the same time, so he took part in this circle. And to his amazement, the language the Blackfoot spoke, and the Cree and the Mi'kmaq, the Algonquin family of languages, was exactly the Rio mode. It was a verb-based language. So I could give you an example. In a dictionary of one of these family of languages, there's a word, and it's one word, and was translated as the sorcerer cures or sings to the sick man. The sorcerer cures a sick man. So it's like the doctor cures a patient. You have a doctor who is an independently existing object, and a patient, and the doctor does something to the sick person, actually does something. So it's our model of the world. But in fact, what this long word says really is singing, or chanting is going on. Or really, the more important thing is singing itself. The song, because the song is a being anyway. So the singing is going on. So really what you have is a process, and out of that you can abstract secondary objects. We'd say the cat chases a mouse. So there's a cat and it's after the mouse, but in their language it's more like his chasing is going on, a chasing chases itself. So this was a language which is very close to Bohm's Rio mode. And then when he began to learn about their worldview, everything is process, everything is transformation, nothing is constant, everything changes. And the best you can do is do ceremonies of renewal. So every day things must be, our connection to the cosmos must be renewed. So you smoke the peace pipe at sunrise. They would never think we cause the sun to rise, it's stupid. What it is we're renewing our harmony between the sun and earth. So it's the idea of renewing harmonies constantly, because everything is in flux.
And that relationship then is also enshrined in not a ceremony exactly, but in an activity that acknowledges the importance of the sun.
Yes, it's acknowledgement, yeah. So in Bohm's discussion with these people, he learned that it's very difficult for them to form categories. They don't like to form categories. I mean, in our world, we have categories. You know, there's fish in this category, and animals, yeah, and this and this and this. But for them, we said, well, how do you deal with fish? Well, there are processes in the water. Well, what about trees? Well, actually, it's the name is the sound that the wind makes in the fall going through the tree. So they said it was very difficult to put on a straitjacket to speak English. And for example, they say you have this strange thing of categories of good things and bad things, where for us this is very bizarre. So in a sense, you know, we divide this binary world up into good and bad oppositions and stuff, and for them, it's a series of processes. So that was very close to David Bohm's view. It was very interesting. I mean, he was very moved at the end, and this was just a few months before he died, to find that he'd had this dream of this language, which was the language of quantum theory, and it was very, and their worldview was very similar. And when he talked to them about ideas, quantum ideas, you know, they were quite open to that. And that's the way we see the world. Yeah.
That was really very interesting. Thanks for that. You mentioned this character, Leroy Littlebear. Could you tell us how you met with him?
Okay, well, he was he was a Blackfoot, but also a lawyer. And in Canada and generally in North America, there's a whole issue of land claims and self-government and everything else. So some of the elders would say the bright young men have to go off and be lawyers. You know, they have to help defend us. So they're like, in a sense, they're like the braves of old, except they're defending with the law. And there was a person, an Iroquois woman, Pam Colorado, who had this idea of the worldwide indigenous network, feeling there was certain knowledge shared by indigenous people all over the world. And she called a meeting in Alberta of people like Native Americans, Australian Aborigines people, Haida people, someone from, from all over the place. And Leroy was the person who phoned me and asked me to come. And at first I said, no, I don't want to go, because I thought I'm going to get into something that's too big. But I went. And afterwards, I started having a number of meetings with Leroy, because Leroy was involved in self-government, and he would come out to Ottawa. I went out to the Blackfoot country and attended the Sundance. And our discussions continued, and with some other Native people. And when I was visiting a place called the Fetzer Institute in Kalamazoo, where I made several visits, and I was talking to the president of that, and he just said, you know, it would be fun. We're walking by the lakes. It'd be fantastic to have a group of scientists and native elders here just talking. And he said, go ahead and do it. So we ran this first circle. Fantastic. And David Bohm happened to be there by chance. So that was the first Native American Western Scientist Circle.
So that sounds like a really interesting thing to be involved with. Could you describe from your perspective what you thought was the most valuable thing to come out of it?
Well, it's hard to say. There are a number, and it was only the first of other dialogues. First, well, one thing with the Native people would say, we spoke to the white man, whenever it was, 500 years ago when Columbus landed. They wouldn't listen to us. And our elders say now is the time to speak again. And the people we should be speaking to are the scientists, because they're the ones that somehow are treated with the most respect and seem to know the most. We must engage them in dialogue.
And maybe on the same wavelength as well.
Yeah,
to some extent.
And I think the thing was, you know, there were a couple of scientists that were very cynical. And at the end of the process, I think they were becoming much more open. So one of the most valuable things was to develop respect for this Native American viewpoint. The respect that this was a disciplined philosophical view of the world. It wasn't just lots of superstitions and things like that. It was a disciplined view of the world, a very interesting one, and one that had a lot in common with ideas in modern physics, like the idea of transformation process, ideas in common. And I think that was a most important thing. I think another really important thing was for the Western people to begin to look back at their own culture and say, oh, what I took as inevitable is a great extent a social construct. Yeah. And I never realized that before. I knew about social constructs, but I never realized, okay, the way I see the world to a great extent is a sort of social construct out of my language, out of my history. And by looking for a moment at another way of seeing the world, you come back and say, how much have I constructed? Yeah. So that enables me to be a bit freer and enables dialogues to reach a new level, a different level.
Were you convinced that scientists described as a quantum realm and the Native Americans described as a spirit realm had any noticeable similarities? Are there any examples?
Yeah, well, one thing would be that they wouldn't always necessarily talk about spirits. They would maybe talk about energies. Okay. So energies, and that fitted very well with, I mean, if you talk to scientists about spirits, they're going to turn them off a bit.
Yeah.
But they often just use the word energies, and they say, what is a molecule? When you take medicine, what do you take? Well, a molecule is a sort of alliance of energies, and when you take it, these energies are released in the body, which was very close to Bohm saying what the medicine is a set of molecules. What they really are is information. Yeah. And you're taking information in the body. When he used to take this acidophilus for indigestion, he'd say, I'm drinking information. Yeah. So there were close metaphors, I think. And one of the most important ideas I think that came across was this prayer. They say, all my relations. All my relations are my relationship with you, my relationship with the members of the tribe, my relationship with the animals, my relationship with the plants, with the trees, with the rocks, with the river, with the beings in the sky, with the beings under the earth. So it expands outwards and outwards and outwards. Ultimately, you're related to everything. So that sense of relationship to everything and that sense of wholeness. So I think that resonated very much. I think one important way of thinking, which is very much one of modern biology, is that really the cosmos is not a machine anymore. Newton talked about well, not Newton, people after Newton talked about the Newtonian clockwork. It was a giant clockwork, it was meaningless. Now we see the cosmos as, or the earth itself, as almost like a living being, like an organic thing, everything related to everything else, very much like the Native Americans, all my relations. So we see the things like bacteria, which I think are unimportant, play an incredible role, keeping the salinity of the sea, keeping the atmosphere going. We are just one amongst many creatures, and we're all interrelated and interdependent. And I think that's a new vision, this interdependence, rather than even talking about Darwinian competition, which may be part of the picture, but really the cooperation.
Symbiosis.
The symbiosis of all living things, which is very much, again, in that Native American vision, always was there.
And when they give this prayer or recognition, or they go through this process, would you say there is an element of gratitude?
Yes, yeah. Very much so, thanking. There's a lot of thanking going. And also another thing would be the sense that they don't own anything. This is not my land. I'm sort of the caretaker. Right. And I'm given this land in trust, and I must look after the land, which is very much like, I think that's across the world in many indigenous societies, that this notion we don't own stuff. It's in our trust. And maybe I have the use of the land at one time of the year to hunt, and someone else may come in here to fish. And so that's their use of the land. So people use the land, and in return. Also this notion of balance, that you take from the earth and you must give back. The rain dance, you're asking the sky to give part of its water. So you must in turn make some sort of sacrifice. Everything is sacrifices and balances. And something very interesting happened when Bohm was there, that some of the elders said that this man is very ill and he has very low energy. And when we do this ceremony, we're going to pass something around. You must voluntarily give your energy to this thing. Everything is in balance, and David will be able to take it. And in fact, this is what happened. And the amazing thing is, at the end, when they played the drum, Dave actually got up and danced, which, if you knew David Bohm, would be a great surprise, because as he said, a little bit further ago, he was not a guy very much in his body, but he danced. I think he'd been given the energy.
Wow.
So this notion, everything is in balance.
How did he feel after that?
Well, I don't know if he knew what had happened, but he certainly looked a little bit different.
Wow. And where do you think his research was leading at the time of his death?
Yeah. One thing that would be really interesting to do, and I've been talking to people in the States at the Fetzer Institute and also at the Templeton Foundation, is to have a conference called The Legacy of David Bohm. I think the time is right to bring people together and say, just what did David Bohm do? What did he achieve? What is the status of the Implicate Order? What's the status of his views on quantum theory? What about his views on dialogue? How has he been of influence to artists and writers? And what about his philosophy? To really get down to it and say, and be critical. I think it's important to be critical too. We're not coming there to praise everything, but to say, critically, what is this? What is that? So I think that's really needed for the legacy of David Bohm, is a conference to bring people together who really know what he did. I think that's the most important thing at the moment.